Here I am. I'm Ben Faber. I'm in Ventura right now, looking out over the blue sky, and it is a great day. It's a perfect day for fruit set. The temperatures are just right. The pollinators are flying. And if you've got 50% of your cauliflower out there, this would be a good day to fly some jib on. So we're going to be talking about fertilizers and water, and then we're going to cover the tools that are in avocado soils, which are really amazing at times. They're illuminating, and you may only go to those tools once in your life, but they are revealing about practices that you're doing in your own orchards. So how to read soil and water reports. And we use leaf analysis and water analysis and soil analysis. And we often get overwhelmed by data. The most common question that I get, probably against all questions that come in from the public and from growers, is where do I go for a leaf analysis, soil analysis? My soil is dead. What's going on with my plant? It's dying. And oftentimes it just relates back to the water and how the water is managed and the junk that's in our waters. And we get excited when it comes to soil analysis. I want to know everything that's going to kill my plant in the soil. And interestingly enough, most common problems that we have in soils are, well, physical problems, aeration of soil and water penetration. So it goes back to the physical property of soil. But the chemical properties that we're most interested in are sodium, chloride, boron, total salts. And so we get carried away with, oh, I've got too much calcium. Well, if you have too much calcium, that's usually a reflection of you've got a lot of carbonates and the pH is too high. So pH is a critical chemical property of soils. And it's a big issue once you get north of Los Angeles. It's much less of an issue when you're down in the San Diego area, where the soils are often of a granitic origin. The pHs tend to be naturally slightly neutral or acid. When you get north of LA, it's a lot of marine deposits, and it's the carbonates. We have a carbonaceous soil, not so much a calcareous soil. We've got carbonaceous soils that are high in carbonates, and it's the carbonates that control the pH at 7.5, 7.8, 8, 8.2, and that makes very difficult for micronutrients like iron and zinc and manganese, copper. So pH, it's the power of hydrogen, pouvoir d'hydrogène, and it controls the availability of a lot of nutrients. And before you plant a soil to avocados, and we've seen a lot of conversion of vegetable soils here because we don't have the labor to pick, to avocados and lemons. And the people will just go in there and plant without having done any soil analysis, and suddenly they see the trees turning yellow. And a lot of times it's because of an accumulation of salts over the years, doing small irrigations on vegetable crops. And you always want to do prior to planting a soil analysis, and it's mainly to look for salinity, how much leaching you need to do before planting or before bedding up, and then the pH of that soil. And so it's really easy to correct pH before you plant, but once the trees are in the ground, trying to change the pH without killing the tree is difficult. So make sure you do a soil analysis for pH and salinity and whatnot prior to planting. So Tim mentioned the potential enhancing ability of boron on avocados when sprayed at bloom or cauliflower stage. More commonly, again, north of Los Angeles, it's more common to see boron toxicity, boron in the water, boron in the soil. And some plants, like citrus, are extremely sensitive and will defoliate. Avocado tends to be a little bit more resilient to boron, but we do see boron toxicity as well. So be careful about using boron as a foliar spray to enhance fruit set. Most macronutrients, and so what I'm saying is right now is that, yeah, we have ability to do water analysis and soil analysis, but just looking at the trees can tell us, you know, a lot as well. So most of the macronutrient deficiencies show up on older leaves, whereas the micronutrient deficiencies show up on younger leaves. Toxicities also show up on older leaves. So this is accumulated salt. This is tip burn. So this is a general salt accumulation that the only way you really can correct it is through leaching, improved water management to remove the salts that accumulate within the root zone. So where do the salts come from? They come from irrigation water, naturally occurring salts, from fertilizer, and we do have avocado orchards along the coast here, and we get ocean spray that brings salts in. The salts that we're talking about, the salinity, the total dissolved solids, you know, these salts are actually nutrients. Calcium, magnesium, chloride for that matter is a nutrient. Sulfate, bicarbonates, boron. We have minor salts such as nitrate and potassium. A lot of our well waters in some areas in the Santa Clara Valley, the Santa Rosa Valley of Ventura, in the Santa Maria Valley, when you get into Salinas, a lot of those well waters are very high in nitrates, to the point where it may be possible to get away without applying any nitrogen fertilizer at all. So anyway, these are salts that are found in well waters, but also our surface waters have got these salts. And depending on the total salinity and the constituents of that salinity, we may need to leach. So soil and water reports are best used for identifying problems. They're not really all that good in trees for managing fertility. So we've got some kind of general guidelines, but the issue with trees is they've got these perennial root systems. They've got this trunk, and they've got a lot of branching, and they've got this mycorrhizal relationship, these fungi that associate with the tree, and all of this works to store and accumulate nutrients in a fashion that's very different from annual plants like a cabbage or even a carrot or something like that, which is a biannual. But you know, annual plants need all of their nutrients coming directly from the soil, a little bit from the air if they're a legume. And there's a good relationship between soil and fertility management. Whereas with tree crops, perennial crops, avocados, citrus, cherimoyas, whatnot, it's harder to manage fertility based on what your soil analysis says, because the soils keep changing. Every time it rains, the nitrogen changes. You know, what's the availability of nutrients? Iron is one of the most common constituents of soils worldwide, yet here we have iron deficiency showing up, and it's the availability. So you can do an analysis of soil, and it may say to add or not to add iron, but it's really the pH that controls it. And if you correct the pH, most micronutrient deficiencies disappear. So pH is an incredibly important chemical property of soil that should be one of the first things we look at. So what do we need to know? We need to know both in water and soil what the boron, chloride, sodium, and total dissolved solids is. And if your water exceeds 1 part per million boron, it's telling you got to do something with that water besides just apply it. You're going to have to work out a leaching program. If your chloride and sodium exceeds 100 part per million, you better get on it. Avocados, as we know, are very sensitive to chloride and sodium, and they're also sensitive to just total dissolved solids, so the total salinity. And when it exceeds 1,000 part per million, you've got to develop a leaching program. Now, in a year like this, where we've had a goodly amount of rain, and last year, where we had so much rain, we were getting asphyxiation to the point there was so much water that in the soil that we didn't have any air, and the roots, which need oxygen, were basically choking on the amount of water, and trees were dropping their leaves. So anyway, this 100, 1,000 part per million is an alert that tells you watch out, work out some management program. It's especially critical in drought years. Just because you can measure it, we can go out and we can spend literally thousands of dollars on soil analysis. Just because you can measure it doesn't mean it's going to mean anything to the plant. Again, it's pH, boron, sodium chloride, and TDS that are the critical issues. There are no good measurements for soil fertility management of perennial crops. And that's a pretty darn flat statement, but it's pretty much true. It works for annual crops, soil analysis for managing fertility, but it's kind of, if you want to use some money, go ahead and do it, but it's not going to help you very much. What we need is leaf analysis. Leaf analysis integrates your gibberellic acid, the sun, how much clouds, the water quality, the soil quality, whether you've got disease, but it won't necessarily tell you why the plant has a certain nutrient level. Okay, so the tree is integrating all these environmental parameters, and you end up with a certain leaf analysis, and that's really also dependent on the amount of crop. So in high crop years, you're going to have a lot of nutrients going into the fruit, and you're carrying that fruit off the field. You've got to replace it. In low crop years, there's less nutrients going in the crop. And so leaf analysis will reflect both on and off years. And it also reflects when we're carrying a lot of fruit from multiple years. So we've got carryover from last year's crop plus the crop that's setting right now. So the leaf analysis is integrating all these different factors, and it's the best approach that we have right now. So the question comes up: what leaf analysis ranges we use? So you can see here that this is the important thing that there's my cursor. So we're talking about ranges. Okay, so in Australia they have a set of ranges. In California we have a set of ranges. New Zealand they have a set of ranges. In Chile and Mexico, Israel, they have ranges as well. The thing is, if you look at these ranges, they really overlap quite a bit. So it's 2.2 in Australia, 2.2 to 2.6, whereas a little narrow range in California, 2.2 to 2.4, 2.2 to 2.6 in New Zealand, Chile, and so on. And so in large part, this is reflecting the difference in the environments in these different avocado growing areas. When you start looking at the other nutrients, phosphorus, potassium, sulfur, they all fall within almost the same ranges. Probably the most different is potassium. Potassium in Australia is 0.75 to 2. In California, it's 1 to 3. 0.8 to 2 in Chile. Potassium is one of the harder nutrients to gauge. There's twice as much potassium going into fruit that's harvested as nitrogen. So in a 10,000 pound crop, you have about 25 pounds of nitrogen being hauled off, but you have about 50 pounds of potassium being hauled off. So in many cases, we're under applying potassium to meet the extractive needs of the avocado tree. I throw this other slide in here. Water quality can also affect the irrigation management. And so we have got these guidelines when the EC, or electrical conductivity, or in other words, TDS, is about 0.7 to 3, 0.75 to 3. We don't really see problems, but we'll have problems when it exceeds 3 decisiemens per meter, which works out to about 1,800 part per million. Sodium, when it's, again, this is about in the range of 100 part per million, chloride in the range of 100 part per million. So we've got these guidelines. The point being made here is that when you have 1.5 acre-feet of water applied at a normal TDS of 1.6 decisiemens per meter, which works out to about 1,000 part per million, there's 10,000 pounds of salt in that. So if you're putting on 3 acre-feet of water, you're putting on 20,000 pounds of salt onto your soil. So leaching is really important, and a soil analysis will tell you how well you're doing leaching. There's no way around salt accumulation other than leaching. There's a lot of claims being made out there. There's a lot of claims that were made last Friday by a guy who came up to me, and you can't get around it. You pray for rain or you manage irrigation to deal with salinity. And there's no amendments that are going to correct it. Gypsum is not going to correct it. That is used for only for removing sodium, and most of our soils are not sodium dominated. They're salinity dominated. So calcium as gypsum really only works when you have a sodium dominated soil. In many cases, we're already putting gypsum on. A lot of our waters are loaded with calcium sulfate. One of the things that happens with salinity accumulation is we see stem and leaf blight. These are, we used to call this Dothiorella, but it's one of the Botrytis diseases, but this is very commonly seen when we have problems managing salinity. Another problem we have is salinity accumulates because of our infrastructure out in the field. When we have a poor distribution uniformity, or even with a well-managed micro-sprinkler system, you get uneven application over the surface of the soil. Right near the emitter, right here, you get a lot of water and you get good leaching. And as you go out from the emitter, there's less and less water in that wetted pattern, and you get to a point where you have a high accumulation of salt. And this salt is only going to move with rain. So in a normal micro sprinkler pattern, you are inherently going to be building up salinity along the margins, and it accumulates to the point where the roots can't take up that water. The salinity is so high. So test is, does gypsum correct soil pH? No, it doesn't. So with that, I would like to go to the tools, unless there's some questions that have come up at this point. No, none. Okay, so what we're going to do is we're going to go to the avocado source.
Okay, here we go. Now we're going to go to tools.
Yeah.
Up here.
Yeah.
Here we are. Can you
Okay.
see
Oh,
that?
thank you. Okay, so go to irrigation scheduling calculator. We're going to start right there. And this is an amazing tool. And it always impresses me how our irrigation practices are often guided by our own psychology. And you know, if it's cold, we don't irrigate. We get all these Santa Ana conditions, and Santa Ana's rapidly will dry out a tree, and it's reflected in the CIMUS calculator that is built into this irrigation scheduling calculator. So if you go to irrigation scheduling calculator and select a crop, we go to avocado, and then we choose the crop coefficient values we're going to use. And so we're going to use the new ones. And then we're going to go to our ET values. And to do that, we go to CIMUS.
Should I try that, or do we just want to say you go to CIMUS? I'm
No,
afraid
no, let's go, because this
okay.
can confuse CIMUS. And then this is actually at the UCIPM website, which is the easiest way to get into CIMUS. And so you go to weather.
Do you see is showing it right here on my screen? Can you see it?
Oh, okay, good. Yeah. And so choose county, and let's choose Ventura County. And okay, keep going. Yeah. And now go to submit. Yeah. And so there's several weather stations here, only one of which has ET values. And so that is the Camarillo A. So click on Camarillo A. Daily data. Yeah. Thank you. And so when we're irrigating according to CIMUS, what we're doing is we're replacing water that has been used by the tree since the previous irrigation date. So, you know, let's say we're irrigating once a week. So let's put in irrigation dates there from March 1st, 2024 to March 7th.
7? Okay.
Yeah. Okay, and then so you see all those blue marks, precipitation, click on them to knock them out, because we're going to get too much data. So click on precipitation, air temp, soil temp, wind direction, relative humidity. Leave the reference ET, click on solar radiation. Okay, so what we've done is there's a whole lot of data there, and what we want to do is find only the data that is going to be pertinent to our irrigation. So go down to number 4, where it says retrieve data. I'm glad you're here, Mary Lou.
I'm glad it's working.
Yeah, it does work. I don't know why I couldn't do it. I had it.
Ben, just to note, it rained on the 6th and filled us up.
Oh, okay. So so it shows ETO, and it my eyes are terrible, but you add those up, and you can put this into an Excel file to make it easier. So anyway, that shows you, what is it, 0.6, 0.17, 0.12. So
0.13, 0.02, and 0.13.
okay, so let's say the average is 0.1. So click out of that. Okay, so in the reference ET, the average has been 0.1 times 7 days. That means it's going to be 0.0 or 0.7. Yeah, thank you. Inches per day, or inches per period. So that it's been 0.7 inches of water loss since the previous irrigation. So we put the crop coefficient in, and we're going to put it in for the month of March. And then our distribution uniformity. Let's say, so this is the amount of water being put out on average by all the emitters. So if it's 100%, which is impossible, that means every emitter is putting out exactly the same. So that means you don't have any coyotes or calcium buildup or broken lines or anything like that. But let's say we've got a DU on average of 80%. So that means 10% are putting out less and 10% are putting out more. And leaching requirement. Yes, we need leaching. Let's say a 10% leaching requirement. And then our how many trees per acre? Let's say 110 trees per acre. Okay, and we've got one emitter per tree. And that next block is if you've got very young trees, you put in, you know, we don't have a canopy that is totally covering the ground. So we're going to be putting on less than would normally be transpired from an orchard. But once trees are about year 8 or so, or anytime you have greater than 65% ground cover, and that's looking from the bird's eye down, it from 0.65 or 65% ground cover to 100 is about the same. So we're not going to put anything in there. We're going to say it's a mature orchard. And then the emitter output is 10 gallons per hour. And grove size is 1 acre. So we're going to calculate, bing. And so, boom, there it is. It says we're going to need to irrigate with 204 gallons per tree. With this system, it's going to take 20 hours and 25 minutes. If you can do that, you set your valve to run that time. The total water requirement is going to be 22,475 gallons. And it's easy. It's wonderful, right? Any questions? How many people have used this calculator? I don't see any hands. Okay, nobody. But it really, anytime, we get into this weird weather pattern, especially in the spring, when we used to not have Santa Ana conditions, it really is valuable to go to Simis to see how the water demand has changed. So, Mary Lou, click out of that and we'll go to another calculator. Oh, how did you determine the leaching requirement of 10%? That is a great question. So this is based on just habit. So, if you've got a DU of, let's say, 50%, where half the emitters are not putting out the average, I mean, you might as well, figure every time you irrigate, you're putting out a leaching requirement because your system is all messed up. But once your DU becomes more and more efficient, once your emitters, you fixed your emitters, every emitter is the same make and model. You've got pressure regulators in there. It's not uncommon for a brand new irrigation system to have a 90% DU. And so again, 90% means 5% are putting out less than the average, 5% are putting out more. And when we have rainfall, you can get by with a 10% leaching fraction. Okay, because you're trying to make up for that 10% difference. When we have a drought situation, you really want to be looking at a higher leaching fraction. And you can go out there with an EC meter, an electrical conductivity meter, And you can get some El Cheapo ones. You don't have to spend a lot of money. But what you can do is in the wetted pattern, after you've irrigated, you can go in with one of these EC meters. And you know, you can get them at online for like $10 or $15 and go in and just poke around in the soil, and we'll tell you what the EC is high or low. You can actually spend $300 or $400 for a more expensive one, and it'll actually tell you, oh, you've got, you know, 1,200 part per million salinity or something like that. But you can look at after an irrigation, what the EC is in that wetted area, and it will tell you per irrigation how much change in salinity is in that soil. And it'll give you an idea of, with your water and your irrigation system, how much leaching you need to do. So typically in water from wells, you're going to need to have at least a 10% leaching fraction. When you're in a district that's getting Feather River water that's coming down and it's pretty darn good, you don't have to be so concerned with the water quality and the need for leaching fraction. You still need it, especially in a drought year. Okay.
Oh, you know, I think, Ben, one thing that would be good to mention is the KC source. If we have the new values and old values, this is something that we probably should take out the old values. The new values were generated from the irrigation project that was conducted with Jim Moster and myself down in San Diego County. And the old values were the values we started that project with. So in California right now, you should use a 0.86, that those values. These may change now that the commission is funding ALI to look at ET again. So we may have new values coming up, but currently we should be using, if you use the calculator, use the new values, not the old values.
Yeah, and also the point's just been made that CIMMYS is just one method of, you know, scheduling irrigations. Soil moisture meters, soil moisture sensors are incredibly valuable, and you really can't use just one tool when you're scheduling irrigations. So soil sensors tell you, oh, it's time to irrigate, it's dry. The thing about CIMMYS is it tells you how much water to apply once it's dry. So they work really well in tandem. And also just a soil tube going around and, you know, taking soil samples and rubbing them around in your finger is quite accurate. It's, you know, it's quite a scientific method, you know, and was the standard up until the 1970s. A lot of irrigation districts used it, and once you calibrate your fingers, you can get pretty darn accurate. So let's go to another tool, Mary Lou, and I want to go to the irrigation water mineral content calculator. This is a fun one. And so this is where you take your water quality statement that comes from the irrigation district or from your water supplier, and it will tell you, click in there under calcium, put in 500 milligrams per liter. So that's typical. 500 milligrams per liter is 500 part per million. So it says here, when you put it in pounds per acre feet. So if you have 500 part per million in an acre foot, you're going to have 1,359 pounds of calcium that goes on. That's 1 acre foot. So just figure you're putting on 4 acre feet, so you're going to be putting on 5,000 pounds of calcium. Again, calcium does not control pH. It's the carbonate or the bicarbonate that does. So magnesium, put in 300 part per million. So this is like putting Epsom salts So in 1 acre foot, you're putting 800 pounds, 815 pounds. So in 3 acre feet, you're putting close to 2,500 pounds of, of magnesium on your soil. Sodium, put in, okay, let's say 50 part per million. That's not uncommon. And so in 1 acre foot, you're putting on 135 pounds, 136 pounds. And so in 3 acre feet, you're going to be putting on close to 400 pounds. Bicarbonate, okay, this is one that controls the pH. So let's put in 400 milligrams per liter, 400 part per million. So you're putting on 1,000 pounds in 1 acre foot. So in 3 acre foot, you're putting on 3,000 pounds of bicarbonate. So this is water that is going to be controlling the soil pH eventually. Sulfate, let's put in 300 milligrams per liter. So calcium sulfate, magnesium sulfate are very common salts. So in 1 acre foot, you're putting on 815 pounds. Or 3 acre feet, you're putting on, again, 2,400 pounds. TDS, let's put in TDS, but let's put in 1,000 milligrams per liter. That's kind of low for stuff up here. So in 1,000 milligrams per liter, you're putting on 2,700 pounds of salt. And so that salt in 3 acre feet is going to be 3 times, it's going to be put on 8,000 pounds of salt. Oh, and chloride. Okay, let's put in chloride. Chloride, 50 part per million. This is very common. 50 part per million chloride. Now, this is an eye opener. So 50 milligrams per liter. And I would hazard to guess this is a very common value, 50 part per million chloride. I mean, it can go a lot higher. It can go to 200 part per million. You rarely see it below 10 milligrams per liter, but 50 is very, very common. No, don't do that. You're going to kill a tree, Mary Lou. Leave it at 50. Okay, so 50 parts per million in 1 acre foot, you're putting on 134 pounds of chloride. 134 pounds of chloride. So in 3 acre feet, you're putting on 400 pounds of chloride. 50 part per million chloride, that's very common. So if you put on 3 acre feet, you're putting on 400 pounds of chloride. Now, I bring this up because we are terribly afraid of muriate of potash. Muriate of potash is, it's called potash because it's the ash left over at burning wood. And so that ash contains potassium, magnesium, calcium, not very much nitrogen, but chloride and potash, potassium. If you live in New York or places that get a lot of rain, you take your ash and you put it out, and it's a fertilizer. Well, if you're putting on potassium chloride, muriate of potash at 50 pounds per acre, you're only putting on 25 pounds of chloride. Okay, so you're already putting on 400 pounds of chloride from the water, but if you put on 50 pounds of potassium chloride, you're putting on 25 pounds of chloride. So that's a drop in the bucket, relatively speaking. So what the point I'm trying to make here is that potassium chloride shouldn't be the fearsome fertilizer that we think of. And especially in a year when we have rain and we have leaching, potassium chloride should be an inexpensive source of potassium, and it's readily soluble. So this is one of the reasons these tools can be so helpful. I mean, it puts something in perspective that, oh yeah, maybe I can think of using potassium chloride. So any comments from the
How about if we put nitrate in? You talked about high nitrate water.
Yeah. So, okay, put in nitrate, and more commonly nitrates, if you look at all of them in this area, it can range from 10 part per million nitrate to 200 part per million nitrate. So yeah, put in 200.
200, okay.
Yeah, put in 200 and go, and it's, you're putting on 500 pounds of nitrate per acre foot. So in 3 acre foot, you're putting on 1,500 pounds. Oh my gosh. No wonder we live in this world that we live in. So put in 10 part per million, which is more common. And so you're even in a minimal amount, 10 part per million. This is very common. 10 part per million is very common. And it's from San Diego to Salinas. And the more well water you use in places like Salinas and Santa Maria and Santa Paula, the more nitrate. And so even in 10 part per million, you're putting on 27 pounds of nitrate in an acre foot. 27 pounds in 3 acre feet is going to be 80 pounds of nitrogen, of nitrate. That's nitrate. That's not total nitrogen. That's nitrate. So nitrate's going to be a tenth of that. So, okay, let's go on to another calculator. Oh, let's see. I wanted to do, let's do the fertilizer calculator. And so this is just a really simple one that tells you what you're going to be paying with different types of fertilizer. So in the primary nutrient, put in nitrogen. Okay, and then and the amount that you want to put on is, let's say, 100 pounds. Yeah, that's 100 pounds of N. And the fertilizer we're going to choose is, let's say, calcium nitrate. I hate calcium nitrate and potassium nitrate. We always talk about these as fast acting in cold soils. Well, calcium nitrate and potassium nitrate both elevate pH. So if you have a problem with pH, using these materials will raise pH. Urea, UN32 actually lower pH. So be aware that the impact of these fertilizers on pH, not just on the nutrient you're putting on. So calcium nitrate, it's kind of expensive. That's another reason why I don't like it. Let's put in, let's say $3 a pound. Okay, and then do a return. And boom. So it says the amount of fertilizer you're gonna have to put on to meet 100 pounds. So you're gonna have to put on 584 pounds to get 100 pounds. The price of that nutrient as N per pound is $17.54 per pound of N. Okay, so the amount of and so you're going to be putting on calcium and as the secondary nutrient. So go up there again and change the fertilizer, calcium nitrate, to urea. I love urea. Yeah. And the price of fertilizer, let's put it at 0.75 cents pounds.
This one, no.
0.75, 0.75. Thank you, 75 cents. Yeah. Yeah. Now do a return. And you can see to get the amount of fertilizer on it's 200 pounds, 214 pounds. The price of the nitrogen has dropped from $17 to $1.61. So this is an eye-opener. I mean, you may only have to do this a few times to get a sense of what you are actually paying for the convenience or fast-acting calcium nitrate. Okay, let's go to another calculator. I love this one. Let's see. Let's do the recommended fertilizer calculator. Yeah, that one. So here, we're gonna choose the different fertilizers. So let's choose a fertilizer. Let's put in, your, oh, let's do ammonium nitrate. And then we just want to look at nitrogen for right now. And so again, in that blue spot, put in 100 above that, the blue spot above that. Yeah, blue square. Yeah, put in 100 and do a return. And so it shows you can meet all of your requirement with the ammonium nitrate. And then go across to total fertilizer pounds. Oh, excuse me. So just after the ammonium nitrate in that white square, put in a 100, and that means you want to meet 100% of your nitrogen requirement from that. Now do a return, and it shows you how much ammonium nitrate you have to put on, 294 pounds. And in the next square, put in it's ammonium nitrates, put in $1 a pound. Oh, and change it to pounds. Yeah. We don't normally buy in tons unless you are ACW or someplace like that. Most of us buy it in pounds, and that's the way most places sell it. So it tells you then, I'm going to be, it's going to cost me $294 per acre to use ammonium nitrate. Okay, so we don't put on just nitrogen. So go up to the top again and where it says potassium in that blue square, put in, no, not phosphorus, but potassium, the K. Yeah, let's put in 100 pounds of potassium. Okay, and then select a fertilizer. And let's do muriate of potash. Yeah, okay. And let's say we want to meet 100% of our requirement from that, okay? Right. And so we're gonna have to put on 159 pounds. And that runs, that's cheaper. That's about 75 cents a pound. Do a return. And then you can see how your fertility management changes. So under the potassium, change the muriate of potash to potassium nitrate. Yeah. Potassium nitrate. Okay. So now we're going to be getting some of our nitrogen from the potassium nitrate. So under potassium, let's say, we're going to try and meet all of the need from the potassium nitrate. And under the ammonium nitrate square where it says 100, put in 50. Well, yeah, put in 50 there, and then go up to where it says 100, we're just below that, and where the whites, yeah, right there, put in 50. Okay, do a return. So if you look down at the bottom, it says fertilizer still needed. So what happens is that we meet all of our nitrogen through that, but when we try and meet the potassium requirement through both the muriate of potash and the potassium nitrate, it says minus 177. That means we're putting on 177 pounds more than is needed because we're mixing our nitrogen sources. Okay. So, it's hard to balance these things once we start mixing the different nitrogen sources. So where it says 385 pounds total fertilizer, put in potassium nitrate, put in $3 a pound. Boom. So you can see how adding potassium nitrate, we've gone from, when we were just doing ammonium nitrate and no potassium, it's $200 an acre. When we added the potassium, muriate chloride, it went to 400. Now with potassium nitrate, it's gone to $1,400. I mean, that's crazy, you know. But I have seen bills of sales from vendors where people are spending $2,000 an acre for their fertility management. And, you know, one of the characteristics of California soils is that they are young, that they are high in nutrition. When you go into an avocado orchard, it's loaded with organic matter. It's all that leaf stuff. It's a system that is recycling itself all the time. This is not nitrogen or New York or Georgia where nitrogen is depaupered, where potassium is, they don't have it. They've got to replace everything in the soil that they harvest. And gosh, we just don't need to do that in California. I mean, when you have a pH of 7, that means you've got a fertile soil. When you have a pH of 7.1, 7.2, 7.3, pH reflects the fertility of a soil and can be too fertile. When you get pHs of 7.5 and 8, that means you got way too much nutrients. So we're more commonly dealing with salinity. That's the reflection. And we're dealing with toxicities of too much nutrients. And so watch out. We don't need to put on as much as we're putting on. So I think that's all I wanted to show in these calculators.
How about the fruit nutrient removal calculator?
Oh yeah, good idea. Let's put in production volume. Put in 3,000 pounds. Yeah, okay. So you can see under calculate 3,000 pounds, you're only taking up 8 pounds, 8.4 pounds of nitrogen. And potassium, look at that, it's 20 pounds. Okay, look at all these other things. I had a wonderful grower who's since passed out in Fillmore, where I told him, oh, there's all this ways of doing nutrient analysis. And he basically says, well, I look at the yield that I get and I just replace it. So I looked at NPK, calcium, magnesium. I mean, he kind of overdid it, but he basically said, I'm harvesting 3,000 pounds or 5,000 pounds or 10,000 pounds. And I basically, during the year, use that as my guide for fertility. I mean, that is a wonderful way to approach it. So, Mary Lou, change that to 10,000 pounds. Thank you for helping, Mary Lou. I don't know why I couldn't get this to work. So calculate. Oh my gosh, now we're taking out 28 pounds. And you look at potassium, it's running, what is that, 67 pounds. Change it to 20,000 pounds. Holy moly. Who gets 20? Well, we've got growers that got 20,000 pounds. And now you're harvesting 56 pounds of nitrogen and 134 pounds of potassium. I mean, that's 134 pounds a year. Now, if you got 2 crops on there, you got 2 crops on there, you got to be feeding both of those. So you're harvesting one and you're feeding another. So you've got to put on an excess of this amount. Plus, it's not an efficient system. You put on 100 pounds and the tree may only, and if you're running it through the irrigation system, then you've got a poor DU. And if you're running an irrigation system on hillsides, you inherently are going to have a poor DU. You got to put on more than you're harvesting. So, I mean, this hopefully puts things in perspective.